Hi everyone, welcome to Gizmo Facts and Happy New Year. I hope you guys are really doing well. Today, I'm going to share some of the new facts about Gizmo Facts. So as you all know that being a Gizmo Facts is one of the um, famous channel in the blogging world. But apart from that, we are going to introduce some of the new paths or directions in technology, and which is data science and machine learning. So basically, we are introducing some of the trainings and tutorials, live trainings in data science and machine learning. So you guys can enroll for those courses, and we'll provide all the links for that. Apart from that, we have already introduced some of the handy books in Python programming language and C++, which will be a good help for the students who are learning or trying to build their career in coding languages, and also for the corporate professionals or IT engineers who are doing some codings in Python and C++. These books are really handy in terms of the languages, and good examples are there which you can try it out. Check that out in the link mentioned in the description below. Apart from that, this today's session, we were going to start our first session in statistics and data science, which is related to a interesting subject, which is adjusted R square, and some of the hidden facts regarding adjusted R square, which I'm sure that it will be a good benefit, a great benefit for the students of data science and corporate professionals as well. So basically, I will hand over this session to my colleague. His name is Abhishek. He's a data scientist as well as machine learning engineer and a great statistician at the same time. So he will take you to the hidden facts about adjusted R square and other facts about data science. So over to Abhishek. Thank you.
Hi everyone, welcome to Gizmo Facts. In this video, we will go into some subtle aspects of linear regression. We at Gizmo Facts provide data science coaching and tutorials all over the world, and also engage in live project assistance on data science topics. In this video, we will concentrate on linear regression and the measure adjusted R square. As all of you know that R square is a measure of goodness of fit for a linear regression model, and it is bounded between 0 and 1. More the value of the R square is towards 1, the better is the fit of the model, and less the R square, the worse is the fit of the model. Now, if you are using any programming language like R or Python, you will see that along with the R square, the adjusted R square value is being reported. The adjusted R square value not only considers the variances or the sum of squares present in the data, but the number of regressors or the independent variables also, because you can always increase the R square artificially by increasing the number of independent variables. Now, naturally the question arises, like R square, is adjusted R square bounded between 0 and 1? This is where even experienced data scientists falter, and they think that because adjusted R square is a derived version of R square, it will be bounded between 0 and 1, but that is not the case. Here in this video, we will see how R square can be less than 0, or for that case even be more than 1. Hi, I'm Abhishek Rai. I have done my statistics from Indian Statistical Institute, and am currently pursuing an executive PhD from XLRI. I have been working in data science for the last 6-7 years as a data scientist, and I'm with Gizmo Facts as a data science trainer. So let's begin. So adjusted R square is given by the formula 1 minus R square into n minus 1 divided by n minus p minus 1. Here n is the number of observations and p is the number of regressors. Now for this to be less than 0, what are the conditions? So in short, we are working backwards. We are writing the adjusted R square formula and finding what is needed for it to be less than 0. So from the formula now, if we take the expression to the other side, we will see that we get 1 minus R square n minus p divided by, n minus 1 here, n minus 1, and in the denominator n minus p minus 1. From here, just we get here by changing the sides of the inequality. Now 1 minus R square here becomes greater than n minus p minus 1 divided by n minus 1, which is 1 minus p by n minus 1. 1 and 1 gets cancelled. So the equivalent condition is R square being less than p by n minus 1. Thus, in a model, if p and n minus 1 is such that R square is less than their ratio. Now, what is p? P is the number of regressors or the independent variables. N is the number of observations or the number of rows of the regression model. If their ratio R square is smaller than that, which means the fit of the model is sufficiently small, then adjusted R square will be less than 0. And we will get adjusted R square to be less than 0 if this condition of R square being less than p minus 1 is satisfied. I'll give you a concrete example. Let us suppose that p is 5, the number of regressors is 5, and n is 11, then p by n minus 1 is 5 by 10 is equal to 0.5. Thus, in this case, any R square less than 0.5 will lead to adjusted R square being less than 0. Now, in this proof of ours, we have assumed something tacitly. What was that assumption? Here, when we changed the sign of the sides of the inequality, we had assumed that n minus p minus 1, this quantity here is greater than 0. Then only we can bring this thing to this side of the inequality, right? So, if this assumption doesn't hold, which means that if n minus p minus 1 is less than 0, which means if n is less than p plus 1, then what happens? I will go back to the formula for adjusted R square, which is 1 minus 1 by R minus R square n minus 1 divided by n minus p minus 1. Now here, if n minus p minus 1 is less than 0, this is negative, and we have a negative sign in front also. So we will get a positive thing added to plus 1. So here adjusted R square will be greater than 1. Thus, if the number of rows of the linear regression model is less than the number of independent variables, then adjusted R square becomes greater than 1. So adjusted R square being greater than 1 doesn't really imply that the model fit is a good one. It actually indicates that there must be some overfitting, because the number of linear regressors being less than the number of rows of the model is always what we want, not the other way around. So as you can see here in our video, we have proved that in particular cases, adjusted R square may be less than 0. It may even be greater than 1. We will come back with many such videos. You can click the link below and subscribe to our channel and stay tuned for more such content. Thank you.